Right, ready to go? Yep. Cool. This episode is the first in a series aimed primarily at teams who have just started in F1 in schools, but we also think more experienced competitors can learn some useful advice as well. In this episode, we'll be discussing car design. Rather than focusing on specifics, this episode is designed to act as a guide to help you along the way to designing a car, with advice about what areas are vital, what areas to prioritise if possible, and what areas are less important when designing a good F1 in schools car. This is Starting Line from Off the Track. Hello and welcome to Off the Track. My name is Peter Russell and today I'm joined by George Stoner.
Hi.
Marcus Vetter.
Hey there.
And Jesse Stevens.
Hello there.
So, it can be hard to design an F1 in schools car from an empty sheet of paper with little idea of what to do and where to start. So, Jesse, where do you start?
So, one of the best pieces of advice I ever got was from one of our collaborators who said, we need to actually ask what we want our car to do. And in our team's case, that was, we want to maximize the points that our car could score. There's like many different ways our car can score points. There's specifications, so all your scrutineering, and the things like engineering drawings, rendering, and quality of finish and assembly, which allow us to do controlled things before the event where we can actually make sure we get those points. And then there's the time trials, reaction racing, and knockout racing. In some places, the knockout racing does not count for points, but in most places it does still. And that's kind of the place where you're not so sure about how your car's going to score points, but you can kind of do that. So once we've worked out our goal of kind of what we want to do, we can then work about how we're going to do it. And this is where we can start going into places like, what are the concepts that we want to explore and what are the things that we want to do? But before that, I always think it's really important to read the rules and follow them. Because they're the easiest 100, 150 points that you're ever going to get in this competition, and you can easily get yourself out of the running of the competition before it starts if you don't follow those rules.
So, in terms of, if you're starting from a blank slate, right, I am a team that knows absolutely nothing about car design. What would you suggest? Where do I start?
Of course, it's important to give the judges what they want. But yeah, basically how to get a car fast is start from the beginning. Try to abstract anything that makes a car fast or slow. Don't take too much inspiration by other teams and try to understand their concepts and make up your own, because then you'll get major advantage later in the R&D process. And also start from the beginning to talk to your manufacturing sponsors and get an overview how are they able to manufacture your components, and then you won't get problems later in the manufacturing process.
I think the process we went through when we were designing a car in Evolve was just getting as much exposure from the competition as possible. And at first we didn't do it right, so that exposure just came from going to the competition and seeing what other teams produce. But I think we could have got a head start by doing what we did later on, which was just watching as many videos as we could of as many world finals as we could, even if there had been rule changes and stuff had to change, just getting as many ideas from what these teams do and seeing these different ideas and seeing maybe what you think might work, what you think might not work, what might be worth experimenting on, trying out, and just getting all these ideas so you can start amalgamating them into your own concepts.
I think that's what George says there alludes to a great point. One solution isn't the best for everyone. There's a lot of different ways you can implement systems and a lot of different ways you can implement various design philosophies. And what that means is that there's not always going to be a car that looks the same as the other cars that can do the exact same job. I know that there are a lot of the teams and the cars that do really well at World Finals usually get copied a lot, and they don't perform the same. So you can obviously tell that there's difference, not just through design, but through the broader process of engineering.
And George, do you get any inspiration from the real Formula One in designing your F1 in schools cars? Is that something you'd advise teams to do?
I mean, it's something to look at because it's a pinnacle of engineering, and they've got focuses on aerodynamics and using advanced materials in the same way that the best F1 in schools teams will do. But the challenges are very different. So if you're looking at a Formula One car, it's got to be producing loads and loads of downforce to get round corners and give it lots of grip. Whereas in an F1 in schools car, you don't want that downforce because you're not going round a corner, and the downforce would just create loads and loads of drag. So you've got to appreciate that it's a very different challenge between the two competitions, so that you can't just, if you made a model of an F1, of a real F1 car and stuck it on a Formula One in schools track, it's not going to do very well.
So technically, now we've got our philosophies, we're looking at teams, maybe real Formula One cars. Technically, how do we go about putting pen to paper? Or is it a case of putting pen to paper? Do we start in CAD? Do we start on paper?
Yeah, in my personal experience, I was someone that tried to learn CAD by doing it. And I'm a very visual thinker, so I can think of ideas in my head and not need them on paper necessarily to bring them to life. But I knew what I wanted, but I didn't learn the skills. So it would force me to learn CAD skills. But that doesn't work for everyone. Not everyone thinks the same. So I know George, if he wants to expand on how he goes about it.
Yeah, so especially starting out the first few years, it would be pencil sketches, which I always really liked doing, and because you could do them quickly and you could explain them to your teammates and you could have discussions quite easily. But as Jesse said, CAD's a great tool, and once, after a few years, I became more confident and fluent in using CAD, it would just be an easier way to come up with a concept. But I think that's only once you've got that fluency.
Yeah, and for me it also was a process because, of course, at the beginning of F1 in schools career, you don't really have the CAD skills you might need to design more complicated or more complex geometry. So it also was a process. In the beginning we started at CAD, but that kind of limited us because then you more like start to think the geometry in how you design it, and not how you want it to be in the end. So later on we started sketching, and even that we also used Play-Doh to explain the geometry that we were thinking of to other engineers, and then later on we designed that in CAD, and so that doesn't limit us anymore in the end.
That's quite interesting. Is Jesse or George, did either of you use Play-Doh or that sort of modelling sort of clay to prototype cars or explain concepts?
We tried something, I think, we used Play-Doh or plasticine or something to try and do something, but usually what we would do is we would stick it onto a car that we already had made. I'm not quite sure if that's what Marcus was talking about doing.
Yeah, I was like referring more like to maybe you got an idea for a side pod because you got inspiration from anywhere, and how you'd adapt that to an F1 in schools car side pod. Yeah, and then you just like mold it.
The main point I found with drawing or modeling like in person was we're trying to communicate ideas. So it's really about learning about how other people think, or if you're with collaborators, understanding and trying to demonstrate your ideas in the simplest way possible. And sometimes that can be in CAD and sometimes it can't be. I know in my team, I didn't really need to communicate that visually with my team member who we worked together with. But not everyone thinks the same. So, yeah.
So, when we're talking about the priorities in designing your car, it's a common belief that reducing the aerodynamic drag of a car is the key to producing a fast car. But how important is it really, Jesse?
Oh, I think it's a very common misconception because of the importance of aerodynamics in Formula One. The aerodynamics in F1 in schools are going to be just as important. Other factors such as wheels, center of mass, and assembly times can really have large effects on the car performance and should be considered alongside the aerodynamics.
Yeah, and one thing I can add to that, like I guess no one of us knows like the actual percentage, even if you can take that, of the factors themselves, like aerodynamics, wheelbase, and stuff. But one thing that misleads a lot of teams to focus too much on reducing drag is that it's so visually. You can use CFD and then just reduce drag forces or even a coefficient, and it's so visually like a visual improvement. And when you test your wheelbase, it's often very complicated, and in the end, it takes a lot of time to get improvement out of that. And working with CFD, you can just sit in front of your computer and get better values.
That's a great point.
Yeah.
One of the things I would like to add, I'm not sure where to, I think. Also, I feel like there might be a massive kind of problem with the way we actually test F1 in schools cars aerodynamically. Until you get to the very highest echelon of F1 in schools teams, most teams don't actually consider the rotational drag of the wheels. And the wheels moving through the air will probably be your biggest source of drag because they're rotating and creating so much problems for the air behind it and air in front of it. So a lot of teams doing testing with static wheels will often only have a very representative model for the very, very start of their race. And that's not realistic, but yes.
Because in the beginning of the race, the wheels are steady, but the car is slow. And if you have a look at the drag formula, that's not even as important as the car being fast, because then drag is way more important. So also try to have a look on how the velocity of your car changes through the race, and take that into your design process as well, because there's nothing steady in the second your car races.
So, George, how do we design a car that is aerodynamic?
I don't know, actually. I'm just
thinking. I'm just reading the questions.
Yeah. I think there's no clear way of designing something or an F1 in schools car that is aerodynamic. I think the best thing to do for any team is to come up with a couple of concepts and test them. If you can test them in CFD, that's great. But if you have the opportunity to test them on the track or in a wind tunnel, that's even better. And just take an iterative approach to designing something or changing something on your design. Does it make it better? Yes, no. If it does, move on with it. If it doesn't, try something else. Just working through those things, I think if you can, looking at some aerodynamic theory, but generally I think the way that I've seen aerodynamic theory applied by most F1 in schools teams, they're not getting it right, or they're not really understanding what they're talking about.
And what is it that they don't quite understand about aerodynamic theory? Should they even be looking at aerodynamic theory? Is that too advanced for like a team that's just starting out?
I mean, it's great to be looking at it, but I mean, I know that even for us, there was stuff we didn't get right, especially just things like the Coanda effect, and when we tried using vortex generators, now that I'm at university and you get to the point where, well, like properly studying fluid dynamics, you understand that you really understand very little. When at a university level, we're simulating something like water just going through a single pipe, you realize that from a academic perspective or whatever, you're not going to get high school age children understanding with physics the flow around their car.
So yeah, I guess that what George said is absolutely right, and perfectly sums up what kind of experience I made from studying at university. Because you won't get a scientific approach, but anyways, you guys want to get fast cars, so don't hinder yourself from looking at theory, but as non-scientifically as it sounds, try to get a feeling for how aerodynamics work, because today it's pretty easy to visualize aerodynamic flow, or how air flows around an object. Not any CFD simulation is very accurate, but if you can validate your testing results with real car tests or within a real wind tunnel, maybe reach out to a university and use their wind tunnel. That's what we did. Then you have somewhat scientific results and can work with that and get somewhat a feeling of how aerodynamics work.
So it sounds like, it's good to have a little bit of a basic understanding about aerodynamics, but not too much. Is that something, Jesse, you agree with?
Well, I'll say this flat out: the fastest car that has ever raced is one of the most poor aerodynamically it possibly could have been. What we actually thought was good testing and solid testing methodology and application of like aerodynamic theory, now looking back on it and understanding the maths behind the more simple aerodynamic concepts that we were trying to employ, it's completely different. And we're kind of at a point where we realize that our car was just fast because of all the other things that we did to it, not at all to do with the aerodynamics. So if we'd known that earlier, we would have worked so much less on the actual aerodynamic development of our cars.
Right, that's quite interesting. Yes, George.
Sorry, I think the other big thing that I think should be mentioned about designing the aerodynamics on your car is don't design the aerodynamics to sacrifice something else about your car. So you see so many cars where they have a really narrow nose, and it looks amazing, and I'm sure it does reduce the drag, but it's so weak that at the end of the track it breaks. And then the next time they race it, they've glued the nose back on and the wheels aren't quite on straight. And so any advantage you've got from having a nice narrow nose, you've completely lost from having your wheels not straight.
So that leads us perfectly into the survival of your car. So Jesse, is it worth designing a car that might, shave off a few milliseconds, or is it worth creating something that is more robust?
Well, in the words of previous engineers, you only design it for the exact amount of races it should do. However, I very much disagree with this theory in this competition. I feel that there's a lot of, especially considering the modelling inaccuracies of the cars that we're designing. So they're very small, the materials aren't uniform, and we're high school teenagers. We don't actually have a very big understanding of actually what we're doing. So the kind of safety factors you need are a lot higher than, say, the pinnacle of Formula One, where you can afford to break down 300 metres after the finish line, right? So I always think that you get the most points by completing all the races. And if your car breaks 3 races in and then doesn't work for the rest of it, there's no real point of designing a car at all then, is there? because you'll get a lot less points than a brick or something that just meets the regulations.
I think also on a point that's not just about points, there's nothing more disappointing, like in F1 in schools, than turning up to the competition and just seeing your car disintegrate on its first race, which is what happened to us once at a regional finals. And at UK regional finals, you only produce one car. And it just broke on its first run. And it didn't even record a time because it broken before it crossed the line. And it was just panic. We were worried that we wouldn't even record a single race time. And which would mean we wouldn't get something like 250 points. So, like, just for your own sakes, design a car that's not going to break.
I would just say, like, the impacts of your design decisions are sometimes maybe put more emphasis on thinking about your design decisions. Like, making your tether guide holders really weak, but not realizing you've made them really weak is a way that your car can easily break, because it flies off the tether line and then smashes into 1,000 pieces or something like that.
Yeah, one thing that helps with that, you can always calculate stuff with how you do it in classical and mechanical engineering, but that's really, really complicated. And you can also use FEM simulation to analyze and simulate the stress on your car. But one thing we learned, if you have the opportunity before a competition, test your cars or maybe an early prototype, because then on the one hand you get so much information and you can test other things, but just for the reason of your car not breaking or breaking, if one of your prototypes doesn't break, it doesn't mean your car in the end will survive the races, but you get some sort of feeling, and you can just cross out this error, because this is like on the one hand, as George said, you don't want it to happen because it's really sad, and on the other hand, it just makes you lose a lot of points.
So it sounds like there's a really strong theme here, which is test, test, test. Now, in terms of manufacturing, a little phrase that's like stuck in my head is design for manufacture from from when I was in the competition. What does that mean, Jesse? Because you were the design engineer who in our team. What does design for manufacture mean?
Well, design for manufacture is kind of self-explanatory. If you need to design it so you can make it. And there's no point having a really complex CAD model of something if you can't actually machine it or 3D print it in a way that's actually safe or strong. So there's often things like putting inside fillets into your car where a drill bit can't get to it, or making sure that you don't have gaps that a tool can't get through. They're the kind of things that are designed for manufacture. And you always have to think about those, because they catch teams out all the time. They caught us out quite a lot as well, because you don't always think about how you're actually going to make the thing until you're trying to make it, and then it goes wrong. So it's a lot better to think about it a lot earlier when it doesn't go wrong, and then you can work on it from there.
George, how did your team make sure that what you were designing you could actually manufacture?
I think a big part of it is looking at what manufacturing equipment you have available to you and what are the limitations of those pieces of equipment. So, for example, we used a router to cut our cars out, and we had to think, okay, like, what if we put a 6mm drill bit on it? We make sure we need to keep everything, all the fillets, to 3mm. And it's like, oh, okay, well, that's a bit bigger than we want, so we need to look at, okay, so we're going to need to make sure that our router can use a smaller drill bit. And then also when we did some outsourcing to other companies, we spoke extensively with them about what they can actually produce, because by knowing what they can produce, we know what we can put into our design. So for example, when we make our wheels, we outsource them to a company that could cut them on a lathe for us. And we wanted our wheels to be as light as possible. So we had to speak to them about how accurate is their lathe, how thin can they actually cut the material. Because if we ask something to be 0.5 millimeter thick and they can do anything to below 2 millimeters, we're going to have an obvious problem, and the wheel that we order is not going to be what we expect.
Yeah, I guess it sums pretty good up what George said. Just try to get an understanding of how the manufacturing process that you are available to work, and then save time to not focus on theories, design, geometry that isn't even possible to manufacture, because if you develop this, you can just like lose a lot of money and time, and that doesn't get into your final car.
There's another thing I was thinking of, which is just because you can manufacture something doesn't mean you should. For example, at the World Finals this year, when scrutinizing the cars, we were looking at, like, as a group of judges, we were looking at this team that had cut on their body these beautiful S-ducts through the body, and we were talking about how they managed to get all the tools and machinery in there to make the cuts, because you couldn't just do it from 2 directions or 4 directions. You needed more angles. And we were amazed by how much effort they must have put into this. But then if you looked at the rest of the car, it wasn't, the paint job hadn't been finished. So it's make sure you design something that's not going to take up your entire time to manufacture, so that you'll be able to manufacture the whole car at a consistent level.
And going on with that kind of point, make sure you can make it in general, but don't spend too much resources on manufacturing. Don't spend too many resources on manufacturing if you don't have to, like that, whether that be time or money or even just collaboration time with people. You shouldn't really need to go that crazy with your 3D printing or that crazy with your machining to a point where you need to hit it from like 8 angles, or you need to use some special type of 3D printing technology that's only available in one very specific spot. It's kind of a waste of time and a waste of resources. So don't spend too much money doing things that aren't needed.
And it's just with this, we're talking about survival and manufacturing. It doesn't just mean, and it might sound like what we're trying to say is just make a brick. Yes, that would be manufacturable and it would survive, but you can produce really beautiful designs that are manufacturable and will survive. So if you look at the top teams at the World Finals each year, generally their cars look impressive, but they've put the time and effort into testing and designing their cars so that they're not breaking and that they've been able to manufacture what they've designed. So it don't let it limit you too much.
So now let's talk about wheels. And Jesse, just how important are wheels?
In some people's opinion, they're the most important component of your car. They're affected by many factors and are responsible with the car's interaction with the track. So it's really important that you get this section of the car design right. We talk a lot about wheels in our episode Wheel Talk, but we're going to summarize our general kind of points that we took from that, and we'll just say right now how we feel that you could design a wheel nice and briefly. So George, do you want to talk about the manufacturing of the wheels?
Yeah, so I think there's a few methods that you see most teams going for when they manufacture their wheels, and that is 3D printing or using a lathe. I mean, I've seen some other methods involving laser cutters and other strange methods, but these are the two main methods. So 3D printing can be great, especially if you've got a 3D printer at school. You can design something pretty quickly, and you can make something that's quite light, cheap and quick, but the problem is they're generally not going to be very smooth. And with the way a 3D printer works, not very accurate, as in being circular, and it's pretty important that your wheels are circular. So I think it's a good method if you're a team that's new. But sorry, I got carried away by saying your wheels should be circular, because that's pretty obvious, isn't it? I don't need to tell teams that.
No, that is actually a serious problem, because like if you design your wheels too lightly, they or too crappily, that they deflect on the track and aren't circular. Anyway, go on. Sorry.
So yeah, 3D printing is great for producing cheap, easy wheels, but the problem is they often aren't very smooth, especially if you're using FDM 3D printing, which is the most common method of using an extruded filament. And they can have problems with being perfectly circular, which is something you really want for your wheel. You can go to more expensive options of sort of sintered nylon, but generally by this point, that will cost enough money that you could start looking at using a CNC lathe to cut your wheels out, where you can guarantee that your wheels will be perfectly round. And generally you'll get a higher quality wheel, but at the expense of extra cost and a longer lead and delivery time.
Yeah, and one thing I'd like to add to the whole wheel topic, it's not only important how your wheels are designed, but also how they are attached to the car, because by not aligning them perfectly, you can lose a lot of time. I mean, as we said in the beginning, we as the podcast don't want to give you any restrictions or any rules. You should do this and then you get a fast car. We just want to share our experience, and from the experience that I've got in this competition, really aligning the wheels perfectly, not getting any glue into bearings and all that stuff is way more important than having insanely thin and light wheels. Yeah, and also just have a look at how the manufacturing works and develop together with your manufacturing partners, because we could like improve the manufacturing of our wheels massively, and in the end you just have a system that's easier to manufacture and also to assemble, and because even if you have high-end components and don't have an idea how to assemble them to your car, those won't get the performance that they're capable of.
And Marcus, you just talked there briefly about wheel alignment. How do teams make sure that their wheels are aligned? Are there jigs that they can use? Are there any special devices?
Yeah, in the beginning we just like had an complete, like, how is it called? Yeah, in the beginning we had an steel axle going through the car, but talking about center of gravity, aerodynamics, and overall manufacturing, this isn't very, let's say, advanced. In the end, we use something we call an axle mounting jig, where you can stick your car in. It's getting aligned by the gas chamber, and we used the points where our car was fixed in the mounting jig as the measurement points for our milling process. So there you have like tolerances way smaller than a millimeter, and then you could attach the single axle parts into the jig and fix them. And then we used some glue that doesn't put too much stress while hardening on the components, so the geometry at all stays the same. And then you have aligned wheels. If you aren't capable of manufacturing such exact and high-end components, then just get creative, because getting wheels to align perfectly is a pretty complicated task, I guess.
and bearings Jesse, how important are bearings?
I am in two minds about this topic because, in my opinion, I think that bearings are really important. But I do not actually think the bearing itself is the most important part of the bearing structure. I think, once again, it's about how you assemble the bearings together. There's no point, especially in our case, where we had $100 bearings per wheel, but because they're so fragile and the assembly process is so finicky, we ended up breaking 16 of our 24 by just putting them together because we couldn't get it nice and aligned. So there's no point a team, especially at the entry level, kind of breaking those kind of components when they need to. So I guess my first word of advice would be stay away from full ceramic bearings until you really need to gain that kind of performance. And then my second kind of advice, so I'm not trying to guide people, but I just think that would be a pretty blanket rule for most teams in the lower levels. And then in a more general sense, just make the bearings that are appropriate for you to implement into your car, or use the bearings that are appropriate to implement into your car. Doesn't necessarily matter if they're the quality, because you can usually get most bearings performing to a good enough standard for this competition. Just make sure they're aligned.
Yeah, and one thing, if you use commercial components in your car, most of these parts have a data sheet where it states how much stress or how much force can you apply to some surface, and like the arrangement, how these components work perfectly. Just try to get this information and work with it. And then the commercial parts will work how they should be working.
And just a quick note on sponsorship deals, especially around bearings, because some companies may reach out to you with deals on bearings, and our general advice is to not agree to anything until you know exactly what you need. That's just some advice from us here. So, Jesse, just in summary from this episode, what have we learned?
Well, we've learned how to make the first steps in designing a good car.
A plus.
I think that was a bit too focused.
A bit too concise for what I was going for, but
You're not wrong.
not wrong.
I think one of my big takeaways from this would be design cars more balanced. Try and design cars with more than just the aerodynamics in mind. Really focus on what makes a car great and what makes a car bad, and then work out how you can design the best car that you want.
That sounds pretty good. Does anyone else, George, Marcus, what's your big takeaway for designing a car?
And one thing I'd like to add is do it your own way. Don't try to get too much inspiration from exterior sources or other teams. And always try to back your decisions with facts or any testing results, because often we made the mistake of just decided stuff about should we use concept A or B without really having data information or factual values. Yeah.
And George, what would your takeaway be from this episode?
I mean, I think it's been summed up nicely. Generally, try and take a holistic approach, focusing on all the areas and focusing on, as Jesse said in the start, what do you really want? Is it you want a fast car, or do you want a car that's going to get you as many points as possible, which at the end of the day is going to help you the most in the competition?
That's brilliant. Well, thank you to George, Marcus, and Jesse for coming onto this episode. And that is it for this first episode of Starting Line. In the next episode of Starting Line, we'll be discussing team formation. So tune in for that one. Thank you for listening to Off the Track. If you enjoyed this episode, rate us 5 stars on Apple Podcasts.
It really does help.
And share the podcast with someone else who may find it useful. Stay up to date with us by following us on Instagram at Off the Track Podcast, and visit offthetrack.net for the latest news.